At 1:23 a.m. on April 26, 1986, reactor number 4 of the Chernobyl nuclear power plant in the Soviet Union experienced an unprecedented catastrophe that would alter the course of history. The rate of reaction in the reactor speeded up. To control the reaction, as experts inserted the rods, an explosion occurred, marking it the world's worst nuclear disaster. The consequences were severe. The explosion and ensuing fire destroyed the Chernobyl 4 reactor and released a substantial amount of radioactive material into the atmosphere. The released radioactive materials, including iodine, strontium, and cesium, had long-lasting effects. The fallout extended far beyond Ukraine, impacting not only the immediate surroundings but also reaching as far as Scandinavia. But what happened on that day? Why did the experts fail to handle the reactions? Let's uncover the chilling story of Chernobyl nuclear disaster. The Chernobyl nuclear power plant, situated around 130 kilometers north of Kyiv, Ukraine, and approximately 20 kilometers south of the Belarus border, started its construction journey in 1972. It comprised 4 RBMK 1000 reactors, each with the impressive capacity to generate 1,000 megawatts of electricity. The tragedy that occurred wasn't a result of an immediate error, but rather a consequence of the inherent nature of the nuclear power plant itself. Before diving into that unfortunate day's events, let's first understand how a nuclear power plant operates. A nuclear reactor is like a powerful heat generator that works through nuclear fission. In this process, a tiny particle called a neutron is aimed at an atom. When the neutron hits the atom, it splits into 2 smaller atoms and releases additional neutrons. This release of neutrons triggers a chain reaction, where these new neutrons hit other atoms, causing them to split and release even more neutrons. This continuous splitting of atoms is what we call a chain reaction. As atoms split during this chain reaction, a significant amount of heat is produced. To harness this heat, the reactor uses a circulating fluid, usually water, to carry it away. This heated fluid can then be used to create steam, which in turn powers turbines that generate electricity. Reactors have special systems to ensure this nuclear reaction happens at the right pace. They use control rods, typically made of materials like silver and boron that can absorb neutrons. These control rods can speed up, slow down, or stop the nuclear reaction and the heat that it generates. It's like having a set of brakes and accelerators to control the entire process. The second important thing to know is the moderator. Its job is to slow down the atoms to increase their chances of interacting with one another. In the case of the Chernobyl disaster, the RBMK reactor used graphite as a moderator and had a positive void coefficient. The positive void coefficient refers to a characteristic in certain nuclear reactor designs where the reactivity of the reactor increases as the coolant, usually water, turns into steam or voids. In typical reactor designs, as the temperature increases, the reactivity decreases, creating a self-stabilizing mechanism. However, it's opposite in reactors with a positive void coefficient. In the context of the Chernobyl disaster, the RBMK reactor had a positive void coefficient. This means that as the water in the reactor turned into steam, the reactor's reactivity increased, leading to an uncontrollable surge in power. On April 26, 1986, something went wrong during a safety test at the Chernobyl nuclear power plant. The test was meant to check if, in the case of a power loss, the turbine could still provide enough electricity for the cooling pumps until backup power kicked in. The goal was to ensure the core stayed cool even without regular power. For this test, the reactor should run steadily at about 700 to 1,000 megawatts of thermal power before shutting down. However, the power dropped to about 30 megawatts. This was happening because of xenon poisoning. Xenon poisoning is a critical phenomenon in nuclear reactors that played a significant role in the tragic events of the Chernobyl disaster. Understanding how xenon-135, a fission product isotope, affects reactor operation is essential in comprehending the events that led to the catastrophic outcome. Xenon-135 is produced during the normal operation of a nuclear reactor as a fission product isotope with a mass of 135. This element has a high neutron absorption cross-section, meaning it captures neutrons faster than the reactor can produce. This results in a gradual shutdown of the nuclear chain reaction. When a reactor is shut down, xenon-135 accumulates rapidly, reaching its peak concentration after about 10 to 11 hours as it continues to be produced from the decaying iodine-135. This buildup of xenon-135 introduces negative reactivity proportional to the power level, preventing the reactor from restarting until the xenon decays and neutron flow resumes. In the case of the Chernobyl disaster, the concentration of xenon-135 started to increase when the power level was drastically lowered. This decrease in power meant that the necessary neutron flux to burn away the xenon was not present, contributing to the sequence of events that ultimately led to the catastrophic outcome. Proper management of xenon poisoning is crucial for sustaining the nuclear chain reaction and maintaining the neutron flux at the desired rate. If not managed correctly, an increased power level can burn away the xenon, causing voids in the cooling water and rapidly increasing the reaction rate, potentially driving the reactor out of control. On the night of the disaster, the power output of reactor number 4 dramatically dropped during the safety test. To rectify the situation, control rods were removed, leading to an unintended acceleration of the nuclear reaction. As the reactor's power output failed to meet expectations, a move was made to remove additional control rods that violated established safety protocols. The minimum number of rods should be 15, but only 8 were left in the reaction. As the power output increased, the water started to steam up, and this also increased the rate of reaction due to the positive void created. The experts now had to control the reaction, and a common decision would be to insert the rods. But here's another problem. The attempt to reinsert the control rods to initiate an emergency shutdown proved fatal. The rod is made from boron, but the tip was made with graphite. The graphite tips on the control rods, designed to moderate the nuclear reaction, exacerbated the situation because graphite accelerates the reactions. As soon as all the rods were inserted, a colossal explosion ensued, instead of slowing down the reaction, engulfing the reactor in flames. This explosion released an incomprehensible amount of radioactive material into the atmosphere, equivalent to the force of 400 Hiroshima atomic bombs. The immediate aftermath of the Chernobyl disaster was characterized by a radioactive plume that extended far beyond the borders of Ukraine. More than 100 radioactive elements and 5% of the uranium fuel, totaling 192 tons, were released into the atmosphere. At 1:26 a.m., the fire alarm sounded, bringing firefighters to the scene. Initially unaware of the gravity of the situation, they attempted to extinguish what they thought was a normal fire caused by graphite. It took over 10 days to control the fire, during which helicopters dropped tons of clay, sand, boron, and lead to contain the spread of radiation. Tragically, one helicopter crashed, claiming 4 lives. Firefighters combating the blaze experienced fatigue and nausea, typical symptoms of radiation sickness. Exposure to high doses of radiation led to the death of 28 firefighters within months. Those exposed to less radiation succumbed to diseases like cancer within a decade. After the fire, the reactor continued producing intense heat, causing the reactor's base to crack. Beneath it lay a water tank filled with radioactive water. If the reactor's heat reached the water, it could lead to a catastrophic explosion. Fearing a third, more massive blast, 3 heroes had to step forward. On May 4, 1986, 3 brave individuals equipped with basic diving gear plunged into the radioactive water tank. Guided only by a single lamp, they located and opened valves to drain the radioactive water. This courageous act was crucial, as a potential third explosion could have rendered the European continent uninhabitable for the next 500,000 years. Europe, from Spain to Sweden, experienced the ominous effects of the fallout, with radioactive rain reported in the United Kingdom. The radioactive dust settling on grass in the hills entered the food chain as cows consumed contaminated vegetation. This in turn led to a surge in thyroid cancer cases among thousands of children. This accident changed the world of nuclear reactions forever. The lessons learned from Chernobyl have shaped the global discourse on nuclear safety influencing policies, regulations, and the public perception of nuclear power. It is an unforgettable chapter in human history that compels us to master the delicate balance between technological advancement and the preservation of the planet and its inhabitants.